Today we're going to learn about angles of elevation and angles of depression. Your learning target is that you're going to solve practical problems. I know you all want to know, when am I ever going to use this? Well, here you go. This is it. So get ready. All right, the angle that your line of sight makes with a horizontal line when you stand and look up at a point in the distance is called an angle of elevation. And you can see from our little diagram here just what an angle of elevation is. You see here's the little person, that's you, and here's your eye. And we're always, whether we're talking about an angle of elevation or depression, we're always talking about the angle with respect to the horizontal. So I'm looking up at the top of this lighthouse. So this would be the angle of elevation. And we're going to use trig to help us figure out what the angle of elevation or depression is, and also how far. Like if we knew, let's take a look at this picture, if we knew how far away he is from the lighthouse, and let's say how tall the lighthouse is, then we could use trig to figure out what that angle is. All right, so that's what's going to be happening. We're still solving right triangles, but we'll have some different pieces of information. All right, let's look at this lifeguard here. The angle that the line of sight makes with the horizontal is the angle of depression. So, you know, if you have trouble keeping these straight, just think of depression as being down, depressed, I'm looking down. But be very careful. Look at your figure here and be careful to note that I'm always talking about with respect to the horizontal. Okay, so this is the angle of depression. Not so many people make an error and they want to call this the angle of depression, but that's not, that angle, the red one I sketched in there, that's not made with respect to the horizontal. So you got to be really careful on your angle of depression that you get your angles labeled correctly. All right, and that's why I put this little reminder here so you will not be the one who makes that error. So now we're just going to work 2 or 3 problems, and that'll be that for this lesson. So get your calculator out. Here we go. You always want to draw yourself a nice little sketch. You're measuring the height of a flagpole. Okay, so we got a flag here. It's a backwards flag, but that's okay. All right, we got our flag. Here's the height of it. So let's call that H. You stand 19 feet from the base of the pole. Okay, so here you are. Here you are. And you're all smiley. Oops, I got you upside down, right? Don't want your head on upside down. I don't know why I did that. Okay, so here you are. And this is telling us you're 19 feet from the base of the pole. So this distance right here is 19 feet. All right, and we want to know, it tells us, okay, the angle of elevation from a point on the ground, all right, from a point on the ground up to the top of the pole. So that's going to be this right here, 64 degrees. Estimate the height of the pole. All right, so we got 64 degrees, and what else do we have? Well, we have H, which is the side opposite, and we have 19, which is the side adjacent, so we're going to use our tangent. We know the tangent of 64 is side opposite, which is H, over side adjacent, which is 19. So now I just have to cross multiply or multiply both sides by 19, however you like to think of it. So I get 19 times the tangent of 64 equals H, and then I'm just going to punch that into my calculator. I'm going to get that H is approximately, let's see, what does it say, to the nearest hundredth? So H is approximately 38.96 feet. That's about how tall that flagpole is. Okay? Same old trig we learned last time. We're just calling these angles different things. Angle of elevation, angle of depression. Okay, example number 2. When a hockey player is 35 feet from the goal line, so let's put our goal over here, and let's put our hockey player over here. That's pretty bad drawing, but anyway, there he is. He's 35 feet, so that means this part's going to be 35 feet right there. He shoots the puck directly at the goal, so bam! he's going to shoot this puck here at the goal. This is our goal right here, in case you didn't notice by my wonderful drawing that that's a goal. The angle of elevation at which the puck leaves the ice is 7 degrees. The height of the goal is 4 feet. So we want to know if that puck is going to go in the goal or is it maybe going to go over. Those are our two choices, right? So what are we going to do? Well, we got our angle of elevation is 7. Of course, we're going to use tangent because we got the side opposite and the side adjacent. So what we're going to do is we're going to say the tangent of 7 degrees. And what we really want to do is, instead of putting 4 in here, I'm going to call this height x. Because by calling it x, I can find out how high the puck is actually going to go at that angle of elevation, right? So I'm going to say the tangent of 7 is the side opposite, which is what we're trying to find out, x over 35. So x is going to be 35 tan 7. So x is going to be not congruent. X is going to be approximately, when I punch that into my calculator, that's going to be about 4.29 feet. So what is that telling us? That's telling us that his little puck that he shoots is actually going to overshoot the goal by about 0.29 feet. So no, buddy, you're not going to make it. No, he shot it over. I'm going to say he overshot. He overshot. That is possible in hockey, right? You could shoot too high. I'm not much of a hockey watcher, but in this case, that's what he did, whether you can do it in real life or not. Okay, because the goal was 4. What's another way we could have done this? Anybody think of another way we could have done this? We could have done, let's see, what if we had done the inverse tangent of 4 over 35. Let's see what that gives us, because that would give us our angle, right? If we do the inverse tangent, let's just look at that. Inverse tangent of 4 over 35. Inverse tangent of 4 divided by 35. So that right there is telling us what our maximum angle of elevation could be to get that puck in the goal. So we would have had to have used the maximum angle we could have used is about 6.5 degrees. Alrighty, another way you could have done that. Hockey player. Hockey player. You know what? Just like in every lesson, I think this is a good place for you to pause and you try to work these next two problems. And then let's come back together and see how you did. Okay, so I kind of stole my own thunder for this next question by doing the previous one the way that I did it with the inverse tangent. So that's all we had to do here. We want to see if the puck goes in, and the way we do that is to take the inverse tangent of the side opposite, which is 4 feet, and the side adjacent, which is 27. And what we get is that angle of elevation is about 8.43 degrees. 8.43 degrees. So what is the question? What is the maximum angle? That is the maximum angle. So as long as he shoots at less than or equal to, maybe we shouldn't say equal to, but we will, because maybe it'll go in. I'm going to say less than, because I don't know if equal to works. Maybe one of you hockey fans can tell me. If his angle of elevation is less than 8.43 degrees, then his puck is going to go in there. That's presuming one of the defenders doesn't keep it out. Okay, now we got a guy. We got you standing over here, and you're seeing a rock climber on a cliff. And this, of course, is my cliff, this great blue cliff over here. You're looking at him at an angle of 32 degrees. Your eye level is 6 feet above the ground, so you see I have that noted here. I'm looking forward to your interesting drawings that you give me on these angle problems. And it says you're standing 1,000 feet away from the base of the cliff. So that's what I have right here, 1,000 degrees. What is the approximate height? Okay, so I labeled the height X. And then I just used my trig ratio that says the tangent of 32 is x over 1,000, side opposite over side adjacent. And then when I cross multiply, punch it into my calculator, I get x is about 624.87. But what you got to realize here, guys, is that x that I found there is this distance right here, right? That's x. That's x because this is the little triangle that I used. So since my eye level is 6 feet above the ground, then I have to add that 6 to know how far the rock climber is off the ground. So when I add my 6 feet of height to x, then I get 630.87 feet. Don't forget to do that if you have the eye level mentioned in the problem. Okay, now, since I just realized we don't have an angle of depression problem, so what I want us to do is go back to the lifeguard. Flip back a page. Let's go back to this lifeguard here, and let me just make up a little problem, and let's see if we can solve it. So how about if I tell you that this lifeguard's eye level is 12 feet above the ground. And how about if I tell you his angle of depression? He's looking down, his angle of depression is 28 degrees. And I want to find out how far he is away, the base of his chair is from the swimmer out there in the water. So what are we going to do? Because, you know, we're accustomed to having the angle inside of our triangle. So what are we going to do here, guys? Well, I got two options. The first one, which is what I typically like to do, is I can think of the ground and this horizontal up here as parallel lines, right? Two horizontals are parallel. So that would mean that this right here is also 28 degrees, right? Because they're alternate interior angles. What else could I do? Oh, well, this would be a right angle, right? This would be a right angle, so I could say 90 minus 28 is 62. So that angle right there is 62 degrees. So I can use either one of those angles. I'm going to use the 28 just because that's what I was given. So let me set up my ratio, and once again I'm going to use tangent. I know the tangent of 28, and of course I'm using this 28 right here, the one that's inside my triangle. What is it? It's the side opposite, which is 12, over the side adjacent, which is x. That's what I'm trying to find. Be very careful here, because what I'm going to do now is cross multiply, and I'm going to get x times the tangent of 28 equals 12. So now I got to solve for x, right? It's not as simple as multiplying 12 times the tangent of 28. I actually have to divide 12 by the tangent of 28. And when I do that, I get approximately 22.6 feet. So the base of his chair is about 22.6 feet away from that swimmer. Hope he can get in there in time if the guy has trouble. I want you to think about this. Come over here. Let me show you something. 28 equals 12 over x. All right, so if I look at that as a proportion, it is a proportion, right? We talked about proportions back in Unit 5, I think. And you remember one thing that I encouraged you to do is to switch your means or your extremes if it makes a situation easier for you. Well, that's what I do in these types of problems. So what I would do here to sort of simplify this is I would switch these two. These are the extremes, right? And if I do that, what I end up with is x over 1 equals 12 over the tangent of 28. So that just saves me a little bit of time from having to cross multiply and then divide again by the tangent of 28. So please don't forget, whenever you set up these trig ratios, you'll have a proportion, and if it helps you, if it makes your work more speedy or more efficient, then you can always still switch your means or extremes to do that. All right, so I think that gets it for us. Those are all our problems. And in your summary, I would encourage you to write that when you are trying to find or when you're using angles of depression in your problems, always remember that you are measuring the angle with respect to the horizontal. And as in the case of the lifeguard, not this angle right here. If I say the angle of depression is 28, that's not the red one. It's the one that's with respect to the horizontal. All right, thank you. We have one more lesson in this unit. It's on vectors, and we'll do that next time.